All right, here we are with the second half of Section 3 for Cybercrime. And we're going to start today by just talking a little bit about how data is stored on a computer in a theoretical way, and then go into how it's stored in a kind of physical way on the actual hardware. And always remember that the explanations I give in this class, this is kind of a lower level introductory course. So I'm simplifying a lot here. Um, uh, Computer scientists, if you're watching this and you're a computer scientist, I apologize for kind of dumbing this down so much and making it so simple. But again, this is just to kind of give people the basic idea of how these work. It's not, my intention here is not to go into a serious amount of detail. This is kind of an overview. So, with data storage, remember, computers don't speak English. They don't even use numbers in the same way we use numbers as humans. The vast majority of humanity at this point uses a decimal system, i.e., we have 0 through 9, and then when we want to say 10, we move one place over to the left and put a 1 there, and then a 0 in the ones place, right? Computers use binary, and so they don't have 0 through 9. They only have 0 and 1. So there's 0 and then 1, and then for what we think of as 2, on a computer in a binary system, that would be 1, 0. So a 1 in the 2's place now instead of the 10's place, and then a 0 in the 1's place. And then 3 would be 1, 1. A 1 in the 2's place and a 1 in the 3's place. And then 4 would be 1, 0, 0. Right? So that's how binary works. So instead of going up by 10 with each spot, the way the vast majority of us do with a decimal numbering system, we go up a 1 for each power of 2. So each digit goes up, the 1's place, the 2's place, 4, 8, 16, 32, 64, on and on and on, right? So that's how binary works. Now, one digit, one kind of spot, either a 0 or a 1, is called one bit of information, right? And computer scientists kind of quickly realized that one bit of information isn't enough to store much data. Either a 0 or a 1, that's not really useful. So they gathered bits together into 8-bit chunks and called those bytes. But byte with a BY instead of a BI, not like byte, but BYTE. And that's 8 bits. And with 8 bits, you have 256 different numbers, all the way from 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1, right? And now with 256 different options, now this is a lot more useful. For instance, we can use 8 bits to have each letter of the alphabet and each decimal number from 0 through 9 can be given its own kind of byte code, if you will. So maybe a 0, 1, 0, 1, 0, 1, 0, 1, we're going to kind of arbitrarily say that's a lowercase a, right? So now if we want to display a lowercase a to the user, we just have to put in that 8-bit byte code, and the computer will be able to translate that binary code into, oh, it wants me to display to my user a lowercase a. Now, as I said before, hard drives have gone through lots of different stages of evolution. Here's a picture of a very old method of storing digital data. But the vast majority of internal drives today are what's known as platter drives. And these are kind of sort of similar to old school record players in that there's a circular platter or disc that spins around really, really, really fast. And then there's kind of, the equivalent of the record needle that kind of goes ins and out and is able to read the data written on that thing spinning around. But one of the differences is on a record player, those would turn at, 33 revolutions per minute or 78 revolutions per minute. Modern hard drives routinely go 10,000 revolutions per minute or even higher. And the other thing is the equivalent of the needle, it's called the seeker head. As it's swinging back and forth, it doesn't actually touch the hard disk. Gets very close, which we're going to talk about here in a minute, but it never actually touches it. But in essence, it works in a similar way, where the platter spins underneath, and then to either read or write, you can move that head in and out, and it can either read or write ones and zeros as it's spinning underneath. Now, this is what the vast majority of desktop hard drives look like on the outside. They're about 3.5 inches wide, maybe an inch tall. But if you take off that silver metal plate there, this is what they look like on the inside. And so two things to notice there. Number one is that it's got this is the read-write head here that can swing in and out, kind of, to come way out here to the outer tracks or swing in here to the inner tracks. And it rotates around this spot here, in and out. And two, it's not just one platter, right? You can see on this one, there's 4 or 5 different platters, and with 4 or 5 different read-write heads. And this thing will spin around at 10,000 RPMs or more, and this thing swings in and out to find different spots on that drive to either read or write those ones and zeros. Now, as I said earlier, the read-write head gets really, really close. Doesn't quite touch, but really close. And when I say really close, I mean really close. And one of the reasons why you should never, ever, ever, ever open up the metal case off of the outside of your hard drive is because invariably you're going to get something in there or on there. Dust, dirt, hair particles, fingerprints, something. And even a fingerprint is taller and larger than the gap between that read-write head and this platter, right? So, I mean, this is a cross-section of a human hair here and here. So we are talking really, really, really close. And one of the other things you have to be careful of with these hard drives is bumping them, knocking them, dropping them, because it's relatively easy for this head to touch that platter, and if it does, it's going to cause a scratch. And if you scratch that platter, you're no longer able to store ones and zeros there, and if you've already stored ones and zeros there, they're now pretty much gone. So you have to be very, very careful with this kind of platter hard drive. Now, that being said, we are slowly moving into a world where we don't need those platter hard drives anymore. We're slowly gaining solid state drives. And if you buy a computer today, chances are it will come with at least one solid state drive. And these have several advantages. So one of the advantages is there's no moving parts. So you'll notice with those old school platter drives, the platter has to spin, the read-write head has to go in and out, and anything mechanical, anything with moving parts is going to wear out over time. So those platter drives will wear out after X number of years. Could be 5 years, could be 10 years, could be 50 years, but they will eventually wear out. Whereas these solid state drives, no moving parts, means they could theoretically last forever. Another advantage of solid state drives is speed. They are much faster at finding and retrieving and writing information than the old school platter drives. Now, the downside is they are much more expensive monetarily, and they usually aren't as large. So like right now, as I'm recording this, I could buy a solid state drive for 1 terabyte, maybe 2. Whereas with a platter drive, I can get 8, 10, 20 terabyte platter drives. So they can't store as much information per drive, and they're much more expensive per byte of information that you can store, but they're faster, no moving parts. And these are kind of the two different kinds of solid state drive at the moment. There's ones that look more like old school platter drives, just without the spinny bits. And then there's ones that look almost more like RAM. They look like just a chip you plug directly into the motherboard. So, one of the things you have to worry about with these drives is remember the fact that basically all of these store data in some way magnetically, right? So, the ones and zeros are stored semi-permanently on these drives. But if you get a powerful enough magnet close enough to any of these methods of storing data, you're still going to wipe everything. So you have to be careful around anything magnetic if you're going to be carrying or using any of these types of hard drives. Now, once I have a physical hard drive plugged into my machine, I need to kind of instruct my computer how to use that drive, how I want data stored on it, what rules I want to follow when storing data on that drive. And this process is called partitioning, right? And usually, the vast majority of the time, you got one physical hard drive and people assign it one partition. And in Windows, those partitions are given letters, right? So right now on this computer that I'm recording this on, I have a C drive, which is the drive I have for Windows. And then I also have like a D, an E, and an F for additional storage. Some of those being solid state drives, some of those being old school platter drives. But you don't necessarily have to abide by that one partition to one drive rule. The easiest way to do it is just to have two different partitions on one physical drive. So I could take a platter drive, say a 2 terabyte platter drive, plug it into my computer and say, okay, I want to create two different partitions. This partition, I'm going to assign 1 terabyte worth of space to it, and it's going to use one kind of set of rules for storing data. Those sets of rules for storing data are called file systems. So I could have one file system on 1 terabyte worth of this 2 terabyte hard drive, and then I'm going to create a second partition on this one physical hard drive and use a different file system, right? And this could be useful if I wanted to have two different operating systems on one physical machine, because a lot of times operating systems will require you to use a certain kind of file system or choose from a small list. But if I wanted to use, say, both the Windows operating system and the Macintosh operating system on one physical machine, I might need to have two separate partitions, each partition with its own different file system on it. And if I could do that with one physical hard drive for each of those, but I don't necessarily need to. If I just had one physical hard drive, I could theoretically put those partitions, those two partitions, on that one physical drive. And they don't necessarily need to be even, right? So if I had a 2 terabyte hard drive, I could give 1.5 terabytes to one partition and a half a terabyte to the other partition. And I could have 4 or 5, 10 different partitions on any given drive. Doesn't really matter. You can also kind of go the other direction and have one partition with multiple physical drives. And the most common way to do this is with a RAID system. RAID, R-A-I-D. It stands for something. I don't know what it stands for. Don't ask me. But using a RAID system, you can have multiple physical drives that the computer kind of thinks of as one drive. And there's all kinds of advantages you can get depending on exactly how you set up this RAID. You can get faster reading speed, faster writing speed. You can get redundancy, so if that one drive fails, you don't lose any data. There's lots of different ways to set this up, and you can research more into that if you're really interested in. But there's all kinds of interesting advantages that those RAID systems can give you by treating multiple physical drives as if they were kind of one drive for the computer. Now, how do these drives connect to the rest of the system? Well, the really old school way to do it, which is almost disappearing at this point, but I figured I'd still throw it in this lecture, is the old IDE system. And this is where you see this gray ribbon. Really old drives will connect via one of these ribbons, one end in the back of the drive, one end into the motherboard. But again, this is, this started disappearing probably 20 years ago at this point, so it's probably almost entirely gone. But if you find a really old device, they might still have those in there. The much more common one today is SATA, which is a small cable that looks like this, much smaller, much faster than the old IDE cables, much easier to install and change out if you're having to do maintenance on the inside of your computer. But then the modern M.2 drives that I said look a lot like RAM, those just plug directly into the motherboard like this. You just have an open slot on the motherboard. You slide that in there and bend it down, screw it down, and that kind of can speak directly to the motherboard through the motherboard's own architecture, rather than having to have one of these cords connecting it from where it's mounted in the case to the motherboard itself. Also helps a lot on just, space savings on the inside of your case. Now, when we first turn our computer on, remember, RAM is empty. Because when the computer's off, RAM is empty. It's that volatile memory thing going on again, right? But we need all the ones and zeros for at least our operating system to be loaded into RAM before we can actually use it as an end user. This is why when I first sit down and turn on my desktop, or even turn on my laptop, not from sleep, but from actually, being off, I can't immediately use my computer, right? It could take me anywhere from 30 seconds to a minute or two before I'm ready to actually log into Windows, right? What's happening during that 30 seconds or a minute or two is the boot sequence. So I can instruct my BIOS, which again is a piece of the motherboard, to kind of do things in a certain order. So I want to load the drivers for my keyboard and mouse. Then I want to look at any attached media to see if there's some kind of bootable device attached to it that has some kind of operating system to it. And if not there, I go to this hard drive, which again on my Windows machine, I've designated C. Go to that hard drive and look in a certain spot for all the ones and zeros that comprise Windows, and load that, display it to the user via the monitor, use the speakers for sound, all those things. And it kind of initializes all those hardware pieces, starts up that operating system, and then displays it to the user. But that boot sequence can be changed around to do things in a different order for different reasons. And if you're dealing with kind of an experienced cyber criminal, you might have to worry about how that boot sequence is set up, where it's set to look for different things, because of lots of reasons. But cyber criminals have been known to do tricky, booby trap kind of things, electronic or digital booby traps, to where you want to make sure you understand exactly what that boot sequence is doing before you turn on the bad guy's computer, so you can understand whether there is one of those booby traps, or make sure that you are booting that system in the correct order. So that is the end of our hardware section. Thank you so much for watching. I really appreciate you.